In accordance with the request of the industrial world for the rationalization of transporting and procuring expenses, large-sized ships have been developed primarily in bulk carriers and crude oil tankers. In particular, the cost of transportation per voyage has been reduced because wide-beam, very large ships have been placed in commission. Then the remodeling of the stern shape aiming at energy conservation has brought an improvement of propulsive efficiency, gaining the maximum 2 knots speed increase with the same output power. On the other hand, these very large ships have still more magnified their maneuvering characteristics, viz. Good turning ability, but poor course-keeping ability. When maneuvering very large ships as typified by VLCCs, ship operators are particularly required to grasp exactly the maneuverability of their own ships and to establish maneuvering techniques more than ever, including speed control. To attain the above challenges, let us consider how to deal with the maneuverability of very large ships. Good turning ability, stable course-keeping ability, and good initial turning and/or course-changing ability are required for ship maneuverability. But turning ability and course-keeping ability are of countervailing nature to each other. Turning ability is characterized by the radius and the rate of turn on the orbital motion of steady turning phase, the former being normalized by the ship length, and the latter by the turning speed and/or ship length. The initial turning and/or course-changing ability, hereinafter called initial turning ability, is defined by the change of heading response to a rudder deflection and the yaw damping response when the rudder is deflected to midship. In other words, this ability indicates whether steerability is favorable or not. The course-keeping ability is the ability to maintain a straight path with the rudder held midship, without applying any counter-rudder. The parameter of block coefficient CB is used for comparing fat ships and fine ships. Fine ships with small block coefficient, such as container ships, constitute characteristic features with good initial turning and course-keeping abilities, but with poor turning ability. On the other hand, fat ships with large block coefficient, such as tankers and bulk carriers, constitute characteristic features with good turning ability, but with poor initial turning and course-keeping abilities. First, let us consider the turning ability. When the rudder is deflected and held at a fixed angle, the turning path of the ship's center of gravity is called the turning circle. The advance is the distance of the ship's center of gravity along the original approach course from the start point of rudder deflection to the point where the ship has turned 90 degrees. The transfer is the distance from the original approach course to the ship's center of gravity when it has turned 90 degrees. The maximum advance is the maximum distance of the ship's center of gravity along the original approach course when the ship has turned a little more than 90 degrees. The tactical diameter is the distance from the approach course to the ship's center of gravity when it has turned 180 degrees. The maximum transfer is the maximum distance of the ship's center of gravity from the original approach course. And the final diameter is the diameter of the ship's trajectory when it has settled down to the steady turning motion. The reach is the distance along the original approach course from the origin of rudder deflection to the center of final diameter. Immediately after the completion of rudder deflection, the ship's center of gravity and aft terminal are kicked out. The kicked out amount on the center of gravity is about 1% of the ship length, but that amount on the aft terminal occasionally reaches more than 15% of the ship's length. The tactical diameter, TD, in a water area unaffected by water depth is shown in the figures, with the maximum 35-degree rudder angle. A fat ship, such as a tanker, is approximately 3 ship lengths, and that of a fine ship, such as a high-speed freighter, is approximately 4 ship lengths. Let us examine the influence of water depth on the turning circle, taking examples of a 280,000 deadweight ton tanker in full load condition. When turning in a shallow water area, the maximum advance increases approximately up to 1.4 times, and the tactical diameter up to 1.3 times, as compared to the turning in deep water respectively. Sufficient care should be taken for the above when navigating in shallow water straits such as the Malacca Strait. Let us examine the turning ability of a 280,000 deadweight ton tanker in ballast and in full load condition. When turning in full load condition, the maximum advance increases approximately up to 1.3 times, and the tactical diameter up to 1.2 times, as compared to turning in ballast condition. VLCCs and bulk carriers should be drawn attention for the changes of turning circles, as they may extremely change their condition, such as draft and trim, dependent on full load or ballast condition. When a rudder is deflected while a ship is advancing on a straight path, the ship begins to turn slowly at first, then increasing its turning rate gradually, and finally turns steadily with constant turning speed and turning rate. At the steady turning phase, the relation between the rudder angle and the steady turning rate is expressed as shown in the figure. Coefficient K is called the turning index gain, and the time needed for the turning rate to develop into 63% of steady turning rate is expressed as T. Coefficient T is called the initial turning index, time constant. Ship A and Ship D belong to the type that both course-changing ability and initial turning ability are either good or poor, and ships belonging to the above patterns are very scarce. Ship B has good initial turning ability but poor course-changing ability. Fine ships of high-speed freighters, such as container ships, belong to the pattern. Ship C has poor initial turning ability but good course-changing ability. Fat ships, such as VLCCs, belong to the pattern. The control of a very large ship will become increasingly difficult when a turning rate has been fully developed with a large amount of rudder deflection. It is important to control the turning rate appropriately by putting over the rudder bit by bit. There is an example of providing an indication of turning rate control where the turning rate should be controlled within 10 degrees per minute for 10 degrees rudder deflection, or controlled within 20 degrees per minute for 20 degrees rudder deflection. Let us consider a case where a ship is changing its course. Due to the turning lag, it is unable to bring the ship on the intended course-changing path, if the rudder is put over when the ship has reached the course-changing point. When changing course, the rudder should be put over before reaching the course-changing point, taking the turning lag into account. The course-changing distance is the distance along the original approach course from the start position of rudder deflection to the course-changing point. The relation between the course-changing distance and the course-changing angle is expressed as shown in the figure. Ship operators are required to acknowledge the elements of turning ability of their own ships, such as the amount of reach, the kicked-out amount on the stern, and the course-changing distance. The following are simulated cases when two full-load 280,000 deadweight-ton tankers are meeting on reciprocal courses. In spite of each taking collision avoidance action by hard over helm to starboard, the collision was unavoidable, resulting in contact with each stern. In this case, each has commenced the initial evasive action at the bridge-to-bridge distance of approximately 0.8 nautical miles. With the assumption that a ship is approaching a berth with a decelerating maneuver, the diagram of speed and distance run is shown in the graph after the main engine stopped when the ship is making 6 knots. Approximate distance run until the speed is reduced to 2.5 knots after the main engine stopped can be obtained from the diagram, because the ship speed of 2.5 knots corresponds with the critical speed at which the rudder effectiveness is nearly lost. The time elapsed for speed reduction is also shown as a function of displaced weight and distance run. When approaching a berth with excessive speed, an order for full astern is required for stopping the ship. During the manoeuvre, the discharge flow of the backing propeller from the lower part impinges strongly on the stern plating on the starboard side, which tends to move the stern to port. Eventually, the ship's head turns to starboard, and it will become harder to keep directional control. In accordance with the Standards for Safety Management System, or SMS, the following precautions are required for decelerating manoeuvres approaching a berth in harbour or an anchorage outside harbour. The ship's speed should be reduced gradually so as to be suited to the remaining distance. The ship should not overrun the target place, and the ship should be brought to stop with directional control being kept stable. Taking safety allowance into consideration, the speed reduction scheme for VLCCs on approach manoeuvres are shown on the graph. In approach manoeuvres, it is desirable to manoeuvre the ship within the speed range of recommendable in the graph, where the function of headway control and directional control are certain to be possible. Ship navigators who have never experienced the handling of very large ships are requested to understand the maneuverability of their own ships. The motion of very large ships cannot be controlled only by the conventional sensitivity of ship handling. Therefore, such ship handling, including directional control, is advisable, as using verified numerical data for maneuvering and the indication of a yaw rate meter. Recently built very large ships are characterized by good turning ability, but extremely poor course-keeping and initial turning abilities. It is to be hoped that you keep safe ship handling in mind, firmly grasping the above maneuvering characteristics.